We're going to be looking at three ideal gas relationships in this section. So pressure, this is standing for pressure right here. Volume, that's going to be our big red balloon. And temperature, there's our thermometer, are all factors that can affect the size and behavior of gases. Now there's one other thing to consider, and that's the amount of gas we have present in each situation. So the amount or moles will be constant throughout the lesson, and so we're not going to consider it. So we'll disregard the moles for now. So three ideal gas relationships can be determined by holding one of these three factors constant and seeing how the other two affect each other. These are going to be the outcomes that we're going to go ahead and prove in this lesson. So let's firstly, in no particular order, let's look at pressure versus volume while keeping a constant temperature. Now before we actually get into the math and equations, it's probably a thought experiment is a good idea. So let's think about a red balloon. What would happen to this balloon if it were allowed to float up high into the atmosphere? So as you go up in the atmosphere, there's less air molecules, so there's actually less pressure. So what happens to the volume of our balloon if there's less pressure on the outside of the balloon? Well, it's going to start to get bigger. There's less pressure, and bigger, and bigger, and bigger, until bang, it explodes. So if we consider this, we're actually going to be able to derive our first gas law. So as pressure decreases, the volume of the gas increases. Again, note the keywords. As pressure decreases, volume increases, and vice versa. Let's just look at one of these scenarios here. So what this means is that volume is inversely proportional to the pressure. So the volume is it's doubling as we half the pressure. The volume is tripling if we 1/3 the pressure. They are inversely proportional. One goes up, one goes down. And we can represent this mathematically. So our volume is inversely proportional to 1/P. Now we also have that constant, the constant temperature to think about. So we're going to stick a little K there. So that K stands for the temperature. All right, that. Now let's simplify this a little bit. So we're going to say V1, instead of the Jesus fish there, we'll just say equals. And I'm just going to put that K up top. Now I've put ones here because there's always sort of a before and an after situation. So this is kind of like the before situation. Now at the same time, there's also an after situation. So we'll call this V2. So V1 could be our balloons on the ground, and V2 is our volume as it's floating up into the sky. And we have the exact same thing going on here. So we have V2s and P2s. Let's simplify this a little bit in the next step. So we're going to cross multiply that P over to the left-hand side. So P1 V1 equals K. And do the same on the other side. P2 V2 equals K. This K and this K are exactly the same. So if both of these expressions are equal to K, then we can simplify this by simply setting P1 V1 equal to P2 V2, and we've arrived at our first gas law. We're going to call this Boyle's law. P1 V1, P2 V2. So all that derivation we just did has ended in this. So let's go ahead and try out this equation in an example problem. A 4.2 liter red balloon. Now I recommend you, when you go through these things, you underline the numbers and the terms that go with it, the units, because the units are going to tell you if it's a pressure, a volume, or a temperature, or something like that. All right, so we want to determine the new volume. So we've got kind of our before situation with this stuff right here. Now let's identify this here. This in liters, that must be a volume, and since the first one we came across, we'll call it V1, and kilopascals is a pressure, so this is going to be our P1. So let's go ahead and fill those into, and it goes on to say determine the new volume, so that'll be what we're going to calculate, and we have it decreased to 70 kilopascals. There we go. Now, before we even proceed, I want to point out that our pressure terms can be in millimeters of mercury, torr bar, kilopascals, there's a few of them. Anyway, so they need to be the same though. So we are working, both values are in kilopascals, so that's fine, we can proceed. If one of these was not in kilopascals, you need to do a conversion that you learned about in Unit 1, make sure they're both in the same, and then you can proceed. So once you have your three variables figured out, I want you to write the equation. Plug in the unknowns. Now at this point, we're going to do a little bit of rearranging. It's probably easiest just to divide both sides by 70. That says 70, and that says 70 as well. And so in essence, V2 is going to be equal to 100 times 4.2 divided by 70. And if you grab your calculator and try that out, you get 6. Now, what are the units on this 6? Well, it's a volume. If you go back over here, you'll notice that this 4.2 is in liters. So if this is in liters, then our answer here is also in liters. Boyle's law, PV, Boyle's law. Let's look at the second one. Randomly here, we're now doing temperature versus volume at a constant pressure. So I want you to think about that big red balloon and a refrigerator. And what we're going to do with that balloon is we're going to shove it in. So what would happen to the balloon if it were placed inside of the refrigerator? So think about that. You put the balloon in, it gets really cold. The molecules inside the balloon start to move slower. They slow down. And as they slow down, the volume of the balloon is going to shrink. So there we go. It shrunk and then it exploded because it got so small. So we have come up with our relationship here. So as the temperature decreases, the volume of the gas decreases as well, and vice versa. So they're either both going up together or both going down together. So that's different from our first gas law. But what we can say is that these are in proportion. They're either going up or down together. So let's do our derivation. Now, so this time we're going to have V is in proportion to T, but we can't forget about that constant. And so let's mathematicalize this. So V1 is now equal to T1 times K, and V2 equals T2 times K. Let's put this all together. Now this one divides out now. So we're dividing both sides by the T. And again, we have these K's, so we can finally put our gas law together. Bam, we have our second gas law known as Charles' law. Charles's law. So VT1, so we've got volumes and temperatures here. So let's apply this gas law now in an example. All right, so a 4.8 liter red balloon, so that's going to be a volume, liters is volume, is filled at 25 degrees Celsius. Celsius is a temperature. So we've got a V1 and a T1 here. Let's make sure we keep these together. And let's determine the new volume of the balloon as we are decreasing to 10 degrees Celsius. So there's our T2. So we have our numbers. So our V1, T1, let's start filling them in. 4.8, 25, unknown, and 10. We'll write our gas law, plug in our values. If I'm going too quickly, you can always pause the video. Now we're going to do some cross multiplying. And in the end, V2 is going to be equal to 4.8. So the way I would cross multiply this is 4.8 times 10. And then you end up dividing by the other one, divide by 25. And we get an answer, if you grab your calculator and try it out, of 19.2 liters. Now let's think about this answer here, 19.2 liters. We said that both of these variables are either going up or down together. So we start with a volume of 4.8 and a temperature here. Our temperature went down. So did our volume go down? It did not go down. This answer is wrong. We have done something terribly wrong, and I hope you noticed what it is. Very few kids make the observation correctly right away. Do we work in degrees Celsius? What was one of the very first things I taught you in section 1? That's convert to kelvins. We need to redo this problem. So 4.8, now there we go. So remember, to convert to kelvins, we're simply going to add the 273.15. So we get 298, and our T2 is actually 283. So when we write our gas law and plug everything in, that's what it's going to end up looking like. And if our temperature went down, our volume should go down a little bit. If you do the calculation, 4.56 is lower than 4.8. So that is our correct answer. So there's your lesson on always work in kelvins. Let's go on to our third gas law. Third gas law, temperature versus pressure at a constant volume. And how do you have a constant volume? You definitely can't use the balloon anymore. So what would happen to the pressure inside of a thermos if the temperature was to decrease? So there's our thermos. That's got a fixed volume, a constant volume. What happens if we jam that out in the snow or put it in a refrigerator? What would happen to the molecules inside? Well, those molecules inside would start to move slower. We know that pressure is measuring the number of times collisions occur on a surface. So if those particles are moving slower, they're going to have fewer collisions, meaning the pressure is going to decrease. So as we've decreased our temperature, the pressure is also decreasing. Okay. So as temperature decreases, the pressure exerted by the gas decreases, and vice versa. So pressure is in proportion to temperature. So this should be the exact same as our previous gas law. So we're not going to need to go ahead and derive this, because all we've done is we've swapped out volume for pressure. So there, in fact, is our third gas law. This one is called Gay-Lussac's law, named after Joseph Gay-Lussac. So pressure and temperature. So let's give this one a go. There's a nice little wrinkle I can throw into this next and final example problem here. So a thermos is at STP. Determine the pressure of the system that the pressure will exert at 150 degrees Celsius. So noted it's not converted. Now STP, we've talked about this before. That was something we learned in the first section. That's a set of conditions. So here's the slide from the first section, and there are the STP conditions. So we know that that's our temperature and that's our pressure as we proceed. This question is not about SATP, so we won't worry about these two in this question. So our pressure, if our pressure is at STP, is 101.3, our temperature is 273.5. We're trying to find our pressure, P2, and we're going to have to convert that temperature because I gave it in Celsius. So make sure you convert that to kelvins. And it's just a matter of writing out your gas law, plugging in your values. Be careful when you cross multiply. So it looks like 100 times 423, and then divide by the 273. And you can check your answer, 156.93. Now again, what are the units on this? Well, back to our pressure of P1, this was in kilopascals. So that means our answer here, that's an A, should be in kilopascals. And there you go. Our temperature went up and our pressure went up too. So there are your three gas laws. So again, be aware of working with the same units when you've got pressure. And don't forget about STP and SATP and converting to kelvins. So go forth and do the homework.